Welcome students to the Centripetal Force Lab. So let's point out some of the hardware features to familiarize ourselves with. So what I'm holding in my hands is known as the Centripetal Force Apparatus. Centripetal Force Apparatus, or simply known as the CFA. And what we have here basically are a couple of masses. These are going to be masses that are going to be caused to rotate within a rotator. I'll show you that in just a moment. Now what we can do is we can set a certain tension due to this spring on these masses due to a tension scale, which if you can read it, runs from right to left 0 to 20 arbitrary units. And we can set whatever tension we want, larger or smaller, acting on these masses by this wheel. So I can rotate it one way or the other, anywhere between 0 and 20. And now the way in which you read it is going to be a matter of consistency. For example, say that I want to read on the left edge of the wheel. That right now is located pretty close to 15 units of tension. But if you decided to use the right edge, it'd be much closer to 10 units of tension. So you're going to be, during this experiment, varying the amount of tension from this spring that's acting on these two masses. And so you're going to be doing them in units of 5. Just be consistent as you change the tension in the wheel. Okay, so one other thing, which is there's a pointer, which is down here. And what we're going to be doing as we cause this apparatus to spin, we're going to be looking for when this pointer pops upward. That's going to happen because as you get this device spinning faster and faster, these masses are going to want to drift outwards, but they're being held from flying off altogether by the tension from the spring itself. Notice how the pointer is popping upwards pretty much as the masses get to the edge of the cage. So let's get this into the rotating apparatus so that you can see the way that that works. Alright, so I've now placed the CFA within the rotating system itself. Alright, so let's look at some features here. First of all, we can turn our power on right here. We want to tighten down the CFA into the system. Make sure that he's locked in. We don't want the entire CFA flying out. And we can control the rate at which this spins. Clockwise or counterclockwise. Let's look below and see how that's done. Alright, this is your clutch plate, and this is your drive wheel. And we can adjust the location of this drive wheel as it interacts with the clutch plate from this speed control knob that's on the bottom. Alright, so I can do that, either cause the drive wheel to move upwards or the drive wheel to move downwards. And by doing so, as we move the drive wheel farther up or farther down on the clutch plate, that's going to cause the CFA to spin faster. One way clockwise, the other way counterclockwise, depending upon if you're operating up or down. So we'll pick one so you can see. So what we're seeking here is a critical piece of information, which is the period of your system, that the amount of time it takes to complete one rotation. So that's where this tongue comes in. So as it intersects the beam of the photogate, U-shaped photogate, and then comes around again and cuts through, we can determine that time, because that time is going to be found from your smart timer. Alright, so let's quickly look at the controls there. We power him on, we select time as we usually do, and we want one gate since we're using one photogate to determine the period. And we know that when we hit start or stop, asterisk is on, that means the smart timer's engaged. Off, it's not. We're going to leave him off for now. You'll see why in just a second. Okay, so now what we want to do is we want to get this guy spinning, and it's going to be pretty fast. It's going to be kind of loud. I recognize this, and you'll see it soon. As in right now, let's go ahead and power him on. And now let's take our drive wheel and let's go to the lower position so you can see how that works. So we're spinning faster and faster and faster. And at some point, what we're looking for are those pointers. We can try to get in view here a little better. There's like an optical illusion where it looks like the pointer is on each side. I'm trying to get a point. Just now, the pointers popped upwards. If I back off the speed a little bit, that is, I'm causing the drive wheel to come back to center a little bit, we saw that the needle popped downward. So the period that you need to register is somewhere between those two. So if I go back to when the needle popped upwards, which is just at that point, I can come back to my timer and I hit the asterisk, and what it does is it's giving me a pretty precise time of 0.1117 for that speed. Well, I can come back and I can back off a little bit, cause the needles to fall back down, get the time again, and I see 0.1166. So we know that the period that we seek is somewhere between those two. So what we recommend is you take the average of those two, and that'll give you the period of your system for when the drive wheel is at its low location or lower location on the clutch plate. Then you're going to do it all over again at this tension for the upward location on the wheel. Alright, so let's say that we've done all that. So we can bring the system back toward the center. Alright, and let's turn him off. So what we did was we found the period of your system, but we know that we need more than that. You know, if you want to get the speed, how fast, that's another critical piece of information, how fast the CFA is spinning, we also need the radius. Well, you're not going to do that obviously while it's spinning. But what we can do is we can disengage the CFA, and what we can do here is we can hang the CFA, and while you're still at that tension that you had, we can hang mass from below until we cause the pointer to move once again. And by doing so, we will achieve the same spring force that was operating on the two masses as it was spinning. Now it's going to take quite a bit of mass to do that. Let's show you how that might be done. So we'll start with one of our bigger masses, and we notice with just that mass right there, that's not enough to make the needle pop. So we want to come and add some more mass, and that's still not enough. We can hang even more from below, and it's somewhere in that neighborhood where we can finally see that the pointer has moved. Right? So you see it's going to be quite a bit of mass. It's in that neighborhood. Of course, you're going to try to be as precise as you can. And so we're going to want to record all this mass that you see here. All the mass that's hanging from below, and also the stamped masses, because they're also contributing to the total mass that's pulling on this spring. And so by multiplying by gravity, change all the masses to kilograms, you'll have the spring force, which should be equivalent to the centripetal force that was operating on the masses as they were spinning horizontally. So while you're at this location, we're going to want to get the radius, because that's the same radius with which it was spinning in the first place. And we can accomplish that with our vernier calipers. We're familiar with this from before. Now this is a little tricky, because what we're going to want to do is get the distance from the center of these two masses to the rotating center. So just to give you kind of an idea where that location is. Alright, so we're zeroed out. And this is easier said than done. You might have a better idea how to get this. But somewhere from the center of those two masses to the center of rotation is in the neighborhood of 50 plus millimeters. So that's another critical piece of information you need for your analysis. And so what you're going to do is you're going to do this several times. We did all of this for a particular tension, and you're going to be doing it for several tensions, 0 to 20, for 5 tension increments. And then in that way you can study centripetal force.